Hi, I'm Alistair and I made this physical electronic version of a well-known word puzzle game. Now, many of you will recognise this grid as the connecting wall round from Only Connect, or you might also know it as the connections puzzle published by the New York Times, which is basically exactly the same game. If you're not familiar with how this puzzle works, there's a jumbled up grid of words that need sorting into 4 connected groups of 4. It's a really simple premise, but what makes it interesting is that there's opportunity for misdirection or crossover when one word can be interpreted in different ways or fit into more than one of the groups. So you'll see that there's several cards here with names of animals on them, for example, but there's only one way of arranging the entire grid into 4 logical groups of 4. Now at this point, if you want to play along, you can pause the video if you'd like and try to solve the wall by yourself. But what I really want to show you is how this puzzle works. So the words are printed onto RFID cards, and behind each of these positions in the grid, there is an RFID reader. Now when the reader detects that a card has been placed, it lights up the corresponding LED underneath. So this doesn't provide any information to help solve the puzzle at all, it's just to confirm that a card can be read successfully. Now if I place all of the cards that belong to the same group on a row, so for example I've got a group of flies, if you spotted it. I've got fruit flies, mayflies, I've also got butterflies, and finally I've got horseflies. Now when a group is formed on a row, you'll see the LEDs change colour instead. There's 4 thematic groups to find, and each one corresponds to one of 4 colours: yellow, green, blue and purple. So here I've made the green group. Now it's worth mentioning that within a group the elements don't have any inherent order, so I can rearrange these cards. For example, let's put fruit here and then butter and may, and that will still form the green group. And also each connected group doesn't have to be placed on any particular row. So I can move all these down, let's swap them over as well. So we've got fruit, horse, butter and may, and now this row will light up green instead. So I'm now going to attempt to solve the whole puzzle. So I've got oil, charmer, I've got skin, and although I have got the word cobra, which is a type of snake, I've also got, snake pit. These are all words that can follow the word snake, and that's the yellow group. Then I've got, what have I got down here? I've got tree, tree pose, warrior pose, dog, and also cobra. Those are all yoga positions. That's the blue group. And finally I've got rat, tiger, rabbit and ox, and these are all Chinese calendar years. And you'll see when the entire puzzle is solved, a relay is activated here which has turned this light on, but obviously you could make this energize or deactivate a maglock or anything you want to give the player their reward for successfully completing the grid. So now let me talk a little bit more about the components I'm using. I've changed the lighting slightly, which means hopefully you'll be able to make out the colours of the LEDs a little bit more clearly. So this is a strip of WS2812B LEDs. Normally it comes in a continuous strip where LEDs are spaced 30 or 60 LEDs per metre. What I've actually done is cut that strip up into individual LEDs and then just spaced them out and connected them with 5-volt ground and a data wire, which is what is carrying the signal that tells them what colour to light up. This is incredibly cheap and easy to buy, and I've used them in lots and lots of projects, so you're probably familiar with this. I've used the WS2812B and just mounted it on the front of the board, keeping the wires exposed to make it slightly easier for you to see what's going on. But obviously in a real world situation, if you wanted to have this in an escape room or something, you would probably want to mount these wires behind the board and simply having the LEDs exposed. Now to show you the back of the board, if I just peel these off, I'll just shake them off, actually it's probably quicker. There we go. Right, there go all the cards. And now if we look at the back of the board, you'll see here I have my array of RFID readers. So these are all MFRC522 readers. These are also incredibly cheap and easy and common to buy. They literally cost about $1 each from Amazon or AliExpress or other online suppliers like that. And I've got them connected via these Ethernet patch cables, which is a technique I've used in the past as well. Now, just to clarify, these are not Ethernet connected RFID readers. They're actually using an SPI interface. I simply use these cables because it's a convenient way to connect 8 different pins to the 2.54mm header row here. So I've got a little breakout shield that just takes the patch cable and allows you to conveniently connect and take those wires to your controller. There we go, that's a bit better job here. And that controller is an ESP32, which I've got down here. Hopefully you'll be able to see that. That is powering the WS2812B LEDs and the readers, the relay on the top of the board. I've also got a button here which is used to activate a training mode. I'll explain in a moment. But also I've got these 4 multiplexers in a line here, and these are what is using the signal lines that are coming in from those readers here. You'll see I've got all 16 patch cables going here, and they're going via the multiplexers before going to the ESP32. Now, to explain why I'm using those, I need to go into a little bit more detail about the specifics of those RFID readers. So as I mentioned, these RFID readers use a serial peripheral interface, or SPI, and that defines the way in which you send data to or receive data back from them. So here's how you typically connect a single RFID reader to an ESP32 controller using SPI. And these wires all have specific purposes. So first of all, we need to supply power to the reader. That's the red and the black wires over this side. Black is ground and red is positive 3.3 volts. Now the green wire carries data from the ESP32 controller to the reader. Now it's normally called master out, slave in, or MOSI, but you might also see it called controller out, peripheral in, or sometimes just data in, written from the point of view of the reader. The blue line, that carries data from the RFID reader back to the ESP32. So that's the master in, slave out, or MISO line, or it's also called controller in, peripheral out. So packets of data are sent on these 2 lines in each direction, and those packets are synchronized based on a signal set on the clock line, which is this yellow wire. Now the controller is always responsible for controlling the clock line, and it's a bit like a metronome or a conductor of an orchestra that keeps a steady rhythm. So on each beat in which the controller changes the clock line's value, a bit of data can be transferred on the MISO or the MOSI lines. Now, SPI interfaces commonly operate at 4 MHz, so that's the equivalent of that conductor keeping tempo by beating 4 million times every second. Okay, great. Now, there's one other wire here, which is this white wire. This is the chip select line, and this is where we start to run into problems. So, SPI is a bus interface, and that means that rather than only being able to use it as a direct connection between a single slave and controller device like here, you can have lots of devices that all share that same interface. So I can add some more RFID readers like this. Now, having more readers means they're going to draw more current, so I've added an external power supply on this side here, rather than rely on the 3.3 volt regulator on the ESP32. They've all got their own separate white select lines going to different GPIO pins, but I've split the SPI lines, the MOSI, the MISO and the clock, and shared them between all of the readers. Now, you might wonder how you can do that. If they're using the same input and output data lines connected to lots of different readers, how do you prevent these signals getting mixed up or interfering with each other? How does the controller know which reader sent which signal? And the point of the chip select line is that it allows the controller to decide which peripheral is allowed to use the bus at any time. And the controller does this by pulling the appropriate device's select line low. So even though all these readers have a permanent wired connection to the controller, they're not allowed to say anything on it unless the controller lets them. And that's how SPI is meant to work, and this is exactly the setup I've used in a tutorial I published about 7 years ago on this channel and has been running happily for years. But here's the problem. A huge number of MFRC522 boards on the market now are actually based on clone chips. They work in almost exactly the same way as the original, and in the vast majority of projects you wouldn't notice the difference from an original NXP chip. However, one way in which the clones typically fail is that they don't fully respect this aspect of the SPI protocol, in that they don't properly release the MISO line when they're not selected. In other words, if you were to imagine this as a class full of nursery school children, it's the equivalent of them not staying quiet even when the teacher has told them that it's someone else's turn to talk. Now, when you've only got one connected reader, you won't notice any difference, but when you've got 2 or 3 or more, you sort of increase the amount of murmuring in the background to the point that the controller can no longer hear the message it wants to. And if you try to connect 16 readers, as I've used in this project, to a single SPI bus, I can pretty much guarantee you it simply wouldn't work at all. So we need some way to explicitly stop readers from using the SPI interface unless we want them to. Basically to enforce the behaviour that should have been present if they were well-behaved devices in the first place. And there's a couple of different ways you could do that, but the option I went for was to use a multiplexer. And this is what that looks like. A multiplexer is basically an electronic one-to-many selector switch. So it has a single connection on this side of the board, which can be routed to any one of 16 different outputs on this side of the board. So I've got 4 multiplexers in a line here. This one on the left is responsible for routing the MOSI signal, then it's the select line, the MISO, and the clock line. And the way in which you decide which one of these outputs is connected to the input on this side depends on the value of these 4 control lines labelled S0, S1, S2 and S3. And here I've got all 4 multiplexers sharing the same control line interface, so they're all going to switch together. So when the controller wants to read a tag from the 3rd RFID reader, let's say, it writes the value 3 to these control lines, and this makes every multiplexer here connect their 3rd channel to the line on this side. So this multiplexer here connects the 3rd reader's MOSI line to the MOSI input onto pin 23. This multiplexer at the same time selects the appropriate select line, which is going to go to pin 5. This one here selects the MISO line from the 3rd reader, which goes into pin 19, and this one here is the clock line into pin 18. So as far as the controller is concerned, it's actually only got a single device connected to each of its SPI lines, and the multiplexer is what is doing the switching as to which one of the readers actually gets to use those lines. Now, I don't think I actually needed to multiplex the clock line and possibly not the MOSI line either, so I might have got away with only using 2 multiplexers. But it does no harm to use all 4 lines of the SPI interface, and it helps to add as much isolation as possible to the circuit. Now, you'll notice here I've actually only connected the first 4 readers into the 4 channels on each multiplexer. That's just because this gets very hard to follow if I try to illustrate all of them. But if I scroll up, you'll see that I've got 16 readers here. And to complete this wiring diagram, what you'd have to do is simply to wire their corresponding outputs into the remaining channels on each of the multiplexers, however many you want. If you really wanted to go wild, you could actually chain the outputs from one multiplexer into another. So you could be controlling 16 lots of 16 channels or 256 RFID readers. But I'm not sure that would make for a great puzzle. And now, just for the sake of completeness, I'll also add in the other components I've got connected. So I've got this push button here, which I use to activate learning mode, connected to pin 26 and ground. I've got a relay that is activated when the puzzle is complete, which is wired into GPIO pin 4. And then I've got my array of WS2812B LE strips, which are wired to pin 4. And they've also got a 1 millifarad capacitor and a 68 ohm resistor on the data line. Now, if you wanted to wire this all up yourself, you could do, absolutely, but it would take ages and there's a very high chance of making a mistake. So what I did was then copy this design into EasyEDA, which is an online tool for designing electronic circuits. So I created a schematic which matched the wiring diagram I just showed in Fritzing, and then I created a PCB for it. Then you can order that PCB to be manufactured, and a couple of weeks later it arrives in the post. Then I can solder on these RJ45 connectors and use those Ethernet patch cables to quickly connect each reader rather than crimping lots of individual strands of cables. This is not the cleanest circuit board design, to be honest. It's pretty much the first attempt I made, but it works, and that's enough for now. If there's any demand for one of these, I might tidy it up and make the design available, so let me know if you're interested. Now, I've been referring to these MFRC522 boards as RFID readers, and in the vast majority of projects that's exactly how they're used, simply to identify an item by reading the unique ID of a card or fob held up to them. But they're not just readers, they're also capable of writing data received from the controller via the MOSI line onto the card, where it's then saved and can be read back again in the future. And in this project, I make use of that functionality to configure the puzzle. Thinking back to the logic of how the connections puzzle works, we don't need to identify the particular card placed in front of each reader. What we need to know is whether all the cards placed in a row are members of the same connected group. So rather than read the card IDs, I'm going to write an additional single byte value onto each card that represents the group it belongs to, 1, 2, 3 or 4. And that's the value I'm going to read from the RFID readers while the game is running. Now that value is written onto the card in a special learning mode. So now let me explain how you write data to the cards to make the puzzle work. Here I've got a stack of blank RFID cards. I've already laid some out, and now I'll just continue to fill up the grid. Now notice when I place them down, the old card, when I put it in front of a reader, lit the LED up. But these blank cards that I'm placing don't have any information assigned to them. The readers don't know what group they're part of, it doesn't read any information, so the LEDs stay off at the moment. And now what we're going to do is we're going to, based on the position I've laid them out in, we're going to write the group information onto the tags. Now to do that, I'm just going to put the serial monitor on so you can see the output from the code. And then I'm going to hold this button down while I reset the ESP32. Now notice that all the LED lights come on yellow to start with, and then it's going to write information onto each card in turn. Now if the group information gets written successfully, that LED is going to turn green. So you can see it's finished, all 4 groups have been written, and now it's changed to the regular run state, so we've got the 4 group colours shown here. I can just take these cards off and just break those groups up. Now if you wanted to play the puzzle in hard mode, you could try and work out how to put all the cards back again, even having written nothing on them, but that's pretty hard, and in fact I've done it wrong already. Now I can't remember how I shuffled those cards around, but it doesn't matter. I put them back, even though they're wrong. I can take the bottom 2 rows of cards off because I can remember how those are set up. But let's suppose that for whatever reason you needed to rewrite that top row of cards. You can just repeat exactly the same process again. Hold down the button, reset the ESP32, and now what it will do is it will write group 1 onto the top 4 cards. The next 4 cards will become group 2, and then from that point onwards the LEDs are going to turn red as there's no more data to be written. But we can carry on using the cards that were written last time. They still got the group information from before. And now let me show you the code that's running on the ESP32 controller that is actually responsible for making all of this happen. Now, it is quite a long code listing in this project. It is longer than my usual tutorials, although it's not actually that complicated. The only real differences from this compared to other RFID projects I've shown is the use of the multiplexers and also the fact that I'm writing data to the cards rather than simply just reading an ID. So I'm going to focus mainly on those two elements of the code, but I shall step through all of it quickly anyway, just so you can see what's going on here. So at the very top here, I'm defining a speed for the SPI interface. Remember that I mentioned that generally SPI runs at 4 megahertz. Here I'm actually slowing that to a tenth of that speed, 400 kilohertz instead, which is still plenty fast enough to transfer information required, but that slower speed will just create a little bit more tolerance in reading the data signal through those long wires, especially as the multiplexers are switching between signals. It should help keep the data integrity a bit higher. So I'm explicitly setting a clock speed first of all. I'm including all the libraries I'm using to access the RFID readers and also to control the LEDs. I'm defining 16 readers for 16 cards that are being arranged in 4 groups of 4, but obviously you can adjust that if you want. Now, you might have noticed when I showed the wiring on the board earlier that the LEDs were arranged in a kind of an S-shaped snake pattern going up the board, whereas the RFID readers are arranged into a more regular index pattern. So to account for the fact that I've laid them out in different ways, here I've just created 2 maps that mean that when I provide an index into a certain reader, so when I'm talking about reader 3, I make sure that that is located on the board relative to the LED that corresponds to it is in the same position. So these are just kind of lookup tables basically that go from an index to a physical position as those components are laid out on the board. Here I define the GPIO pins that are connected to all of the components which I laid out, and then I also define the location in the way in which the data is laid out on the RFID card. I've got to specify the memory address where we're going to store that byte of group information. So we're going to store it in block 4 of sector 1. You don't need to worry too much about these values. You shouldn't need to change them if you're using regular RFID cards, but we're not going to write to the very start of the card memory. That's reserved for keys and things that are used for authenticated access to the card. We're going to write to block 4, but don't worry too much about that. That just means that when we read and write to the cards later, we know that we're accessing the same memory address. We get some globals. Now, unlike in previous projects where I've had multiple RFID readers, and generally in those cases I've created a separate instance of the reader class in order to be able to access each one individually. Here I'm actually only creating a single instance of the RFID reader class. As far as the code is concerned, it's actually only dealing with one reader, because the ESP32 does only have one output that is going as far as the multiplexers, and then it's the multiplexer's responsibility to physically connect the appropriate reader beyond that into that interface. But that's kind of happening outside the ESP32's control, and it doesn't need to know about what's happening there. So we actually only create a single instance of the MFRC522 class here, but then here we do keep arrays to keep track of whether a card was present at each one of the readers, what group it belonged to, and also the RGB value of each of the LEDs. So these are all arrays containing one element for each of the readers, but then the reader object itself, which is how we'll access the methods to write and read to the card, we're actually just going to reuse the same instance of the object here, and like I say, use the multiplexers to physically connect the appropriate reader hardware into that instance. Let me start getting onto our methods. So this is a very, very simple method here. This simply lets us specify a channel number, so 0 up to 15 for each of our 16 different channels, and this will write the appropriate value to those control pins of the multiplexers to connect the appropriate reader into the SPI interface so that we can then read it. This is the value that is called as part of that training function at the beginning that writes data onto the cards, and specifically it writes a byte that is either going to be 1, 2, 3 or 4 of the group that the card belongs to. So what we do here is, first of all, we check that a card is present, and also that we can read the serial number of the card, so it's a valid card value. We don't want to try to write data to something that's not going to be able to be read back again. And then just for a little bit of debug information, we will read the card ID. So remember I said that I don't use the card ID in any of the game logic, but just for the sake of debugging purposes, if you want to make sure that you're keeping track of cards that have been assigned to groups and things like that, we'll just output the ID here. And then this is a little bit different than normal. When you are reading the ID of a card only, you don't need to authenticate to have that kind of level of access. That's a read-only field that you can access without any additional information. When you're writing data onto a MIFARE card or something like that though, you do have to provide a key. You have to authenticate with it. So we're going to use the default key value here, which just involves creating a key and then populating the first 6 bytes with the value of FF in hex. And then we're going to authenticate onto the card by supplying that key and the necessary information we specified at the beginning as well here with the UID that we just read. So this is going to allow us to create an authenticated, or attempt to create an authenticated connection to the card. We're going to make sure that that was okay. If it was so, we're going to create the data packet that we want to write onto the card. This is going to be a 16 bytes, but we're actually only going to use the first byte of that 16-byte buffer, and that is going to be the group data, so the value 1, 2, 3 or 4, whichever group we want this card to be assigned to. And then we will write that value onto the card. We'll just make sure that that is okay, and we'll turn off the reader again, and then we'll return true. So this whole function here is only called when we use the learn mode by holding that button down, and it gets called repeatedly for each of the readers for each of the cards to assign the correct group onto that card using, as I mentioned, an authenticated connection. So that's slightly different from the way in which I've used these readers in the past, and you might not have seen that before. This is the setup functions. This obviously happens when we first start loading the code. We'll create a serial interface, we'll initialize our GPIO pins, we will take a reading from that learn button pin and decide whether we're going to be entering learning mode or not, or whether we'll just run straight into the regular runtime mode. We'll initialize our set of WS2812B LEDs, and depending on whether we're in learning mode or not, we will either color them yellow or we'll just color them in white. Either way, what happens is we'll actually turn them all on just to test that they're working. Anytime you have a kind of a puzzle controller that has LEDs on it, when you reset it, I typically just make them light up or show some sort of pattern. You can use that as a status indicator if you want to indicate what mode the puzzle has been set into, which I'm doing in this case. But you can also just use that as a way to check all the LEDs and wiring are working. And then we'll turn them off again here. Then we start the SPI bus. We set the multiplexer pins to be outputs, which it's going to be using. And then we initialize all of the readers. So we're going to be reusing this same MFRC522 instance. We've only got one of these, remember, but what we're going to be doing is we're going to be looping through all of the readers, all 16 readers in turn, and on each iteration through this loop, we're first going to call the select channel function, and that was the one that we've already looked at earlier, that is responsible for setting the control signals to all of those 4 multiplexers. So we're going to write, let's say, reader 1, reader 2, reader 3, reader 4 in order, make those multiplexers switch across to physically connect the corresponding reader, and then when that reader has been connected, we're going to initialize it. And this initialization function here, this is exactly the same as you will have seen used in many RFID projects, including all the ones I've done in the past. This is the standard initialization procedure. The only thing that's different about it is that we have added this extra step at the beginning to be able to run it multiple times with different readers. Okay. Now, if we have entered learning mode, once we've initialized all the readers, this is where we're going to need to call that write group data function that we just looked at above as well. And we need to decide what group to write to each card to. Now, this is quite straightforward really, because what we're going to do is we're going to count the index number of the reader. We're going to divide it by 4. And because this is an integer division here, so the readers that have the index numbers 0, 1, 2 and 3 divided by 4 are all going to give the value 0. The index numbers that are 4, 5, 6 and 7 are all going to give the value 1, because that's how integer division works. You ignore the remainder. And then we're going to add on one more to that. Now, the reason I'm adding the 1 is because I'm treating group 0 as a special case. That means that the card has not been assigned to a group. So whereas most variables used in programming languages are 0 based, on this case I'm using 0 as a special case, and I'm going to call the groups 1, 2, 3 and 4 instead. So based on the position of this reader, where it's physically laid out on the board, and remember that that is then corresponding to this index number here. So we've actually started at the bottom right hand corner as the index 0 and the top left is 15. But passing it through that map means that I can loop through and make sure that I'm using the LEDs and the readers in the same index system. And what I'm going to do is I'm going to loop through all of them, work out which group the card that is placed on this reader should belong to. If it's in the top row, it's in group 1, then 2, then 3. Then I'm going to call this write group data function, which is the one that we saw defined up here. I'm going to pass it the group corresponding to the row in which that reader is placed, and then I'm either going to turn the LED green if it was successful, or I'm going to turn it red if it failed. Okay, and that is the end of the setup function. So I'm only calling that once. If you want to rewrite the cards, if you want to overwrite them into a different group, you need to reset the ESP32 and hold that button down to enter learning mode again. Once the program is running, we're in the loop function here, and I no longer check the value of that learn button anymore. It's only done once in the setup function. So what do we do in the loop function? Well, actually it's not that dissimilar from what we just seen above. Again, we loop over every reader in turn, we select each one of them. So this is the instruction to the multiplexers to connect that reader into the bus, which means that we can then address it using the methods of the MFRC522 class. And we're going to check whether there is a card present at the currently selected reader, and we're able to read the card value. But we are not going to be using the serial value that we read. This merely checks that we're able to read from the card. Instead, we're going to read the group data from the card. Now, we haven't got to the group data function yet, but it's basically the matching function of the write group data that we defined above, and it's incredibly similar. Once again, we need to create an authenticated connection to read from the user data section of the card. We're using the same key as before, so it's a 6-byte value with just FF in it. We'll create a temporary buffer for the data that we read back from the card. We'll create an authenticated connection supplying the key that we just defined. If that was successful, we will call the MFRC522 method here, and we'll use it to populate the temporary buffer that we defined up here. And then what we do is we simply return the first byte from the buffer that we read, because that is where we stored our group ID value. So that's read group data, and that gets called here. If the value that we read from group data is not equal to 0, because remember I said that was what I was using as my special case, and it is less than or equal to the number of groups, that means that we've read a valid value from this card, and either there wasn't a card present before, or there was a card present before, but it was in a different group than the group that we last knew about. So basically all this is saying that we've been able to read a group from this card and it was different from what was known about this card before. That's when we need to update all our arrays. So we'll update the card groups array with the group that can be read from the card currently. We'll update the card present array to say yes, we have been able to read a card here. Then we'll call validate groups, and finally print group status. So now let's take a little bit look at what they do. Actually, now I'll tell you what, before we do that, we'll just get to the end of the loop function because we're nearly there actually. This is the counterpart to this function here. So this said that a card is in range and could be read. If that's not the case, but there was a card present at this reader on the last time we checked, well, that means that the card has been lifted off. So what we need to do here is update those arrays again. The group assigned to this reader in the array is now reset to 0. So this means that there is no group known about in the reader that's had a card removed. We'll update that to false. And once again, we'll validate groups and we'll print the group status. So between them, these two cases here deal with the cases of a new card being placed or a card being changed or a card being removed. And then we just turn the reader off before we go on to the next one. Okay, this is a very quick function here. So the MFRC522 library as supplied comes with a function called, I think it is new card present. That only works if a new card is placed in front of the reader. But for this puzzle, we don't need a new card to be placed. We just want to know, is a card there? So this is a new function called is any card present rather than is new card present. And it just returns true if there is a card there. Read group data we have just looked at. Validate groups. Okay, so here we have the game logic, or the puzzle logic as it were, that actually checks now whether all these values, we've been populating these arrays with group indexes and whether the card's present, LEDs and things like that. This is actually the puzzle logic bit that tests, have we got a row of items that all belong to the same group. So what we'll do here, we'll start off with a Boolean value of all correct. This is every card is correct, and we'll assume that that is true to start with, but we might well be disproving that theory in a minute. And then this time we loop over the groups. So we're no longer looping over each individual reader, all 16 of them, we're just going to loop over the 4 groups. And we're going to work out what the base index of this group is. So effectively this means the index of the reader that is on the left-hand most position of this group, if you want to think of it like that. And we're going to create a variable which I've called expected group. Now, there is no expected group at the outset for any row to have. As I said, you can make the green row of items, the yellow of items, and per row on any row you want. But if you think about the way that a human would check whether these values are the same, one logical way of doing it is, well, let's look what group the card at the leftmost of this row is a member of, and then let's see whether all the other cards are a member of the same group. So where I've put expected group here, what I'm actually going to do is I'm going to read what group is the card that is the leftmost of this group a member of. And we will expect all of the other cards in this row to then have the same group information assigned to them. That's what I mean by expected at this point. It's not expected that this particular reader is assigned to this group. It's more that this is what we expect having checked what a value of one card in this row is, and particularly it starts off being the card on the left-hand most edge. Okay, and we'll just have another Boolean so it's valid. If the expected group was 0, well, that means that the card wasn't present. And if any card is missing from this row, we know that it can't possibly be a valid group. So we can set that to false straight away. If there was a card present at the beginning of this row, and we were able to read what group it belonged to, what we then need to do is to check over all of the other cards in this same row and see whether they belong to the same group or not. And that's what we do here. So we count from 1 up to 4 and we check whether the group assigned to the card at that position is different from the expected group that we read on the first card. And if that's ever true, then we know this is not a valid group, because we know that at least one of the cards in the rest of this row didn't have the same group as we expected. And in that case, we can set valid group to false. So we loop over all this functionality here for each group. And having determined whether it is a valid group or not, we also then need to set the LEDs for this group. So that's what we do here. If there was no card there, we turn the LED off, which is the same as setting it to black. If there was a card there, but it didn't belong to the same group as everything else, we turn it white. Or if this was a valid group on this row, we get the corresponding group color, which is called from a little helper function right at the end here. So I've just defined some RGB values for yellow, green, blue, and kind of purpley pink. And we set all of the LEDs equal to the group color corresponding to the number of this group. Okay. And if any individual group is invalid, that also means that as a whole, the wall also is not correct. So we can set that based on that. Once we've looped over all the groups, we can then say if they were all correct, the puzzle has been solved. Let's write a high value to the relay pin, and that's where you can turn the light on or turn a maglock off or whatever else you want to do. In any other case, however, we know that there is at least one card either missing or has been misplaced in its group, which has made that row incorrect, and that means we turn the relay pin low. I think the final function, which I haven't described yet, which is this one, this is really simply just for using for debugging purposes, but it is what you saw output in the serial monitor in the last video where I was just showing me training the cards and then placing them on the screen. This is the function that we were seeing that was generating that output. It simply loops over each reader in turn, and when it gets to it, it prints the group information associated with the card last read from the that positioned reader. And that is a very quick tour of that code. So that just about brings me to the end of this video. Now, I've made RFID projects in the past, and there's also loads of great resources and tutorials out there for how to use these common RFID readers. But even though I was trying to recreate one particular puzzle in this project, I was also trying to demonstrate some topics about working with RFID that I don't see demonstrated very often. The first of those is how you can write and then later retrieve just arbitrary data onto any of these RFID cards. And the second one is how you can use a multiplexer to address an array of a large number of RFID readers, all using a single ESP32 or Arduino microcontroller. So even if you're not interested in creating this specific puzzle, hopefully those two concepts are something you'll be able to adapt and transfer over to your other projects and use them in a completely different way. Now, as always, I'll be uploading the code listing that's running on the ESP32 as well as the wiring diagram over to my Patreon account. And if you'd like to access those or the resources for any of the escape room projects I've demonstrated in this channel, please do head over there and check it out. If you're an existing Patreon subscriber of mine, thank you so much for your support. I really do value it, and it does enable me to continue to create these tutorials each month, so thank you. And if you don't want to, or if you're unable to support me there, that's fine too. I will continue to upload these tutorials to YouTube each month, and you can copy down the code listing yourself as I demonstrated it all earlier. Now, if you've got any questions or comments about this project, or if you've got any suggestions for future projects you'd like to see me make, do please write those as well, because I always love to hear from you. And other than that, I just want to say thanks very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.